We're going to continue to solve exponential and logarithmic equations today, and one of the things we're going to talk about is also your change of base formula. So if you have log base b of u, you can always rewrite it into a different base. Go log base, whatever base you want, of u over log base of that same base of what was your original base. Typically, we use the change of base formula to change things into log base 10 or your natural log, because those are the two that work on your calculator. So typically we would go log base b of u and write it as your common log of u over the common log of your base, or the natural log of u over the natural log of your base. Now, some people seem to think that this is a true statement. It is not. So don't get confused there. So using our change of base formula to rewrite this one, we can go the common log of the 20 divided by the common log of what was our base of 2. And we could type that in. Now, if you wanted, we could have also have changed it into natural log stuff. And if you type in your natural log stuff here, you still get the exact same answer. Does not make a difference. So here we're going to solve this exponential equation. It's exponential because we have our variables in the exponent. Now, we did some problems like this earlier, but we were always able to get the same base on each side. But there's no way we can easily rewrite 4 and 5 and get them into the same base. So all we're going to do is apply a log to each side. Now, in some problems where our variable was an exponent before, we changed it from the exponential form to the logarithmic form. But that's when we had variables only on one side or the same base. Now we have different bases and we have variables on both sides. So we'll apply a log to each side. Well, now that you have exponents after logs, we can use the clog rule and put the exponents in front of the logs. Now, we have log of 4, which is some messy decimal. Well, this is just a number. We could distribute that through here and go 2x log 4 plus 3 times log 4. Same idea here with the log of 5. It's some messy decimal. So we could distribute that through and we get this. Now, as a side note here, if I gave you 2x plus 5 is equal to 7x minus 8, to solve a problem like this where you have x on each side, just like we do here, you'd try to get all the x's on one side, like subtract the 7x from both sides, and get the things that, like the 5, that don't have x's on the other side. Well, we're going to use that same approach for this particular problem. We're going to try to get everything that has an x on one side. So I'm going to leave this here. This has an x, so I'm going to try to take it to the other side. So I need to subtract an x log 5. Now, this does not have x's. So I don't want it left on the left side where there's x's. I want to take this to the other side. So I'm going to subtract my 3 log 4 from both sides. Still having my minus 2 log 5 here. Now over here at this one, we would combine these together because they're like terms, and then we'd have x times something and we'd just divide. Well, these are not like terms. We can't combine them together. However, you'll notice that x is a common factor, so we could pull that out. Well, now we just have it as x times something. Well, to get x totally by itself, all we have to do is divide, and we would get this. Now, this is what your calculator-ready form is. I'll be looking for this on almost all problems when you take your test or your final. So, if you don't have the fraction feature in your calculator, you got to put the whole top in parentheses and hit divide, put the whole bottom in parentheses. If you have the fraction feature in your calculator, hit the fraction feature, type in the top, type in the bottom, and you will get this. I'm only expecting these two here. Most of your answers will come from the calculator-ready form. Only a small part of your points will come from the decimal approximation. Now, could you have used properties of logarithms up here on top and on the bottom to simplify it down to get this here? Yes. Do you need to? No. So, here we're not really doing anything new. We've done problems like this before in the last lesson. So here, not everything has logs, so you get all the logs on one side. So subtract this log over. Then you have a log minus the log, so you could write it as one log and divide what's afterwards. Then you can go from the log form to the exponential form. There's no base written here, so then it's assumed to be base 10. So we'll take our 10, swing it over, hits the 2 up as the exponent. Now we have a fraction equaling a fraction, so we could just cross multiply or multiply both sides by our least common denominator. Either way, we end up getting this. And then it's pretty easy to solve from here. We could subtract a 5x from both sides and add a 300 to both sides, and then we get 301 divided by 95. Now we'd actually have to check to see if this works in the original problem. Well, we know this is a positive number, and 5 times a positive number plus 1, we know it's positive there. But what about plugging it in over here? So you might want to go ahead and do the decimal approximation of this, but just think, this is about 300, this is about 200. But it's not quite 200, so if it was 300 over 200, that's 1.5. So since the bottom's a little bit smaller than that, it's slightly more than 1.5. 2 times slightly more than 1.5 is slightly more than 3, minus 3 would still be positive. So it would work. But if you wanted to do the decimal approximation and plug it in over here, that would work too. So we need to look at this problem. We have 2 to the power minus 6 times 2 to the power equaling 6. Now, we could work it out just with this 2 to the power, but for a lot of you, you're going to find it easier if you think of that 2 to the power and replace it with like an a. You'll find it easier to work with. So I replace that with an a. Now this will be an a to a negative exponent because of that negative after that 2. Now, we've solved problems like this before. You have a negative exponent, so you know that negative exponent goes down to the bottom. Notice the exponent on this 6 is positive, so that 6 stays in the top. And you know we don't like our exponents or variables in the bottom, so we can multiply everything by a to get it out of the bottom. A times a is a squared. A times this is 6. A times this over here. So now it's just a nice normal quadratic. So we could set equal to 0, and we've solved quadratics before. Sometimes they factor, but the quadratic formula will always work. So we could use quadratic formula here, simplify what's in your root, simplify your root of 60, which is a 15 times a 4, take the square root of that 4. Notice you can take a 2 out of everything top and bottom, and we would get this, or we get the negative root. So at this point, I would come along and take this a is equal to 2 to the x. Now that I got a by itself, I would replace this a with 2 to the x and finish the problem. So go 2 to the x is equal to that, and 2 to the x is equal to that. Now, this is almost the square root of 16, which we know is going to almost be 4, and 3 minus something almost 4 is negative. Remember, an exponential is never negative. An exponential is always positive. So if this side's positive, this side's negative, this side or equation doesn't work. However, this side is positive because it's 3 plus something. This side's positive, so we should be able to solve it. But our variable's in the exponent, so therefore we're going to use logs. We're going to apply a log to each side, and I'm going to choose a common log. You could choose a natural log. It would not make a difference. Now you're going to have a variable after, or as an exponent after log. So if it's an exponent after log, you can put that exponent down in front. Now we just have x multiplied by something. So to get x totally by itself, all we'd have to do is divide by log of 2. And we would get this. This is referred to as your calculator-ready form. then you could go ahead and type it in to get your decimal approximation.